Good morning. Today we will continue our lecture about the crystalline defects in structure, and today we will tell about the linear defects, uh, the specific linear defects about the dislocation. Linear defects include violations of the correctness of the structure along the line, not necessarily a straight line. The transverse dimensions of a linear defect don't exceed one or several interatomic distances, and the length can reach crystal size. Linear defects can be stable and unstable. Unstable linear defects include chains of point defects, vacancies, or embedded atoms. Such defects cannot exist for a long time. Stable linear defects in crystal are dislocations. A dislocation is a linear imperfection such as the breakage of or shear of atomic layers, which disrupts correctness of their alternation in the lattice. As noted above, plastic deformation in a crystal does not occur instantaneously but gradually along certain atomic planes in certain directions. In other words, in the process of plastic deformation, at such an instant of time, it is possible to detect a moving boundary between regions in which plastic deformation has already occurred and an area where there is no deformation yet. This boundary is the line of dislocation. The ends of this line either emerge on the surface of the crystal or form a dislocation loop inside the crystal. Depending on how the sections of the dislocation line are oriented with respect to the displacement vector, the edge and screw dislocations are distinguished. Here. And if it is at the bottom, then it is negative. The position of the center of core of negative dislocation represent as T, and the positive dislocation this symbol. The concept of a screw dislocation was introduced in 1939 by Burgess. Let's make an incision in the crystal along the plane ABCD and arbitrarily conduct shift to the right front of the crystal down to one lattice period, as here. Form to which such a shift step on the upper face doesn't pass through the entire width of the crystal, ending at the point B. Since the incision ABCD only reaches the middle of the crystal, then the direct part cannot move entirely towards to the loft by one lattice period. The displacement of the right side towards to the loft decreases in the direction from point A to B. The top atomic plane is curved. Similarly, the deformed second atomic plane from above, the first part of it from the front edge is shifted by one lattice period and merges with the third, and etc. This figure shows the arrangement of atoms in two vertical planes passing directly on either side of the shear plate ABCD. The resulting shift of the described area of imperfection is called a screw dislocation. As atoms are in it for spiral staircase. Screw dislocation, as well as in the screw, can be left and right. They turn to each other as mirror. The right dislocation and this back the left dislocation. The main differences of through dislocation from the edge ones. The first screw dislocation is parallel to the shear, and the second screw dislocation can be formed by a shift of any crystallograph plane containing the dislocation line on any surface ending with this line. Dislocation cannot end inside the crystal. Consequently, the dislocation line may close or terminate within the crystal on its surface. Some parts of dislocations have edge or screw dislocation, but much of it is not parallel and not perpendicular to the shear vector. Such dislocation is called mixed. Here you can see the creation of through dislocation, and here you can see the arrangement of atoms along the line of screw dislocation. On this slide, we can remember, you must remember these properties, it is very important. The main properties of dislocation. Dislocation, depending on the orientation of the shear vector, can be edge, screw, and mixed. Dislocations cannot break off inside the crystal, they exit to the surface of the crystal or they close themselves to themselves. Creating the dislocation loop. And the third dislocation can move along the volume of the crystal with mass transfer. This movement is called clumps without mass transfer. To estimate the degree or distortion of lattice caused by dislocation, one should compare a perfect crystal with an imperfect one containing a dislocation. To do this, use a construction called the Burgess contour. Burgess vector is a measure of lattice distortions due to the presence of dislocation in it. It determines the dimension of dislocations, the shift effects of mobility of dislocations, and thus is the main quantitative characteristics of dislocation. To access the degree of lattice distortion caused by the dislocation perfect crystal should be compared with imperfect one containing the dislocation. For this purpose, a structure called Burgess contour is used. Burgess contour is closed loop here of an orbital shape built in a real crystal through the sequent bypass of the defect from atom to atom in a perfect crystal region. Here, the ideal crystal. This is a real crystal with dislocation and with the vector Burgess. Vector Burgess is characterized by several phases. The first, vector Burgess is normal to the line of edge dislocation and parallel to the line of screw dislocation. In case of mixed dislocation, the angle between the dislocation line and Burgess vector has a different value. The second, Burgess vector of defects of non-dislocation time is equal to 0. The third, Burgess vector is the same all along the dislocation line, that is an invariant of the dislocation. Since the Burgess vector is an important quantitative characteristic of the dislocation, it is necessary to mark it so that the report reflects the direction and magnitude of the vector. The Burgess vector is usually written as next way, where HKL as a symbol of crystallograph direction of the Burgess vector. I hope you remember the crystallograph indexing. And A is the lattice parameter in this direction. Usually it is distance between the atomic plane, and n is integer. Power of dislocation is a value determined by the formula, this formula. Thus, Burgess vector is a measure of lattice distortion caused by the dislocations. Its numerical value is characterized by power. Dislocation density is the number of dislocation lines intersecting a unit area in the crystal. Its dimension is centimeter minus 2. Dislocation density is important technical characterization of qualitative properties of the crystal. In crystals ground by conventional methods of melt crystallization, the dislocation density is about 10,000 centimeters minus 2. By varying this density can be reduced to 1,000 centimeter minus 2. As a result of plastic deformation, the dislocation density increases in several times. Best semiconductor crystal obtained by growing have the dislocation density maybe 100, maybe 1000 centimeter minus 2, and even more per square centimeter. There are dislocation-free crystals. To understand these figures better, we note that when the dislocation density is only 1000 centimeter minus 2, the total length of dislocation lines in 1 cubic millimeter of the crystal is 1 kilometer. It is very big figure. And at the end of our lecture, please look the film about the dislocation. I hope it will be interesting for you. It will be interesting for you, and thank you for your attention. Have a nice day.